or light bulb, Thomas Edison type light bulb, where the wire just gets so hot that it starts glowing. And in that one, it's kind of a good example because you've got all these different molecules that are vibrating. They're vibrating at different speeds in different directions, so they end up putting out all different frequencies, all different wavelengths of light, and your eye sees all of those, and we say, well, that's white light. Where in fact you've got a mixture of infrared and ultraviolet and all the different colors of visible light. You've got all that stuff going on at the same time. So if you want a light to glow red, like a stoplight, well, you can have an incandescent bulb and you can put a red filter in it, a filter that's transparent to red wavelengths of light, but it's opaque to the other wavelengths of light. So this light bulb behind it then is putting out all these different wavelengths of light, and your filter is absorbing all of them except the red, so that the person who comes up to it sees the red light glow. Well, that means huge amounts of energy are going into producing light that you don't need at all. You know, it just gets absorbed by the filter. That all just becomes heat. And the same thing on the green light, and the same thing on the yellow light. And again, when we get into the quantum mechanics unit, we'll talk about how an LED works. But an LED light is monochromatic. It only puts out one wavelength of light. And so when they invented red LEDs, you started seeing them around all the time, because one of the first things, I'll get your question in a second, the first thing that they did was that, well, you know, these stoplights are incredibly inefficient because you're taking 99.9% of your energy and just turning it into heat just to get that little bit of red when the thing's on. Well, if you have a light that only produces that red light to begin with, your energy consumption goes way, way down. So I don't know if you guys remember, it seems to me like it's just yesterday that those things started showing up, but they may have been around for your entire lifetime. But red lights started showing up, and they would be those, you know, instead of just one big red bulb, you had a whole bunch of little bitty tiny red bulbs that all glow together. Well, those are all red LEDs. And then the green ones showed up next, and they started being able to manufacture green LEDs efficiently. And so those came in. And yellow ones are still not as common, but you still see some yellow ones now, but now you're starting to see yellow ones. Now, the thing to me that was really significant and really cool, and again, this happened recently. When I look, if I go back and Google it online, I'll find that it was like 15 years ago, but in my head it was still recently. I can remember when some company announced that they had found a way to manufacture blue LEDs at a cost-effective, in a cost-effective fashion. Why was that such a big, hairy deal that they were now able to manufacture blue LEDs? The hint is they already had red and green.
The highest frequency.
What are the three colors that the human eye is sensible to?
Oh,
red, green, and blue. And so by combinations of red light, green light, and blue light, you can make all the true colors, you know, all the colors out of those three. So if you can now manufacture red, green, and blue LEDs cost effectively, you can make full color, thin monitor screens, flexible screens, all the little tiny, you know, the thin projection screen, you know, all the screens, you know, cathode ray tube televisions disappeared like almost overnight because we can now produce red, green, and blue LEDs. And so they use way, way, way less energy, and you can produce pure colors, really vivid, really realistic, because we've got those three. Okay, so I kind of got off the subject there, but I think I was here, then I was going to go there, then there, and then there. So, Derek, you got a question? Okay.
So when you're talking about whenever it brings like the UV rays coming into the sunscreen and it turns it into heat, so essentially it's converting it from UV to infrared.
Yes.
So it's just like changing the wavelength actually on it.
Yeah.
And just re-emitting it back out.
Mm-hmm. Right. Which kind of, in these fluorescent lights, that's kind of what happens there too. The gas on the inside emits a lot of UV. Then if you've ever broken one of these, the inside of the glass is covered with kind of a powder. Mm-hmm. It's called a phosphor. And what that phosphor does, it absorbs the high energy UV, turns some of it into heat, and re-emits the rest. Well, the rest now has a little bit less energy than it had before, so it's no longer UV, and the energy level that's right below UV is visible light. And so that re-emits light down in the visible range so that we can see it.
Purpose for this technology, they actually have it in use and stuff like that.
Yeah. Okay. Mm-hmm. You had a question, Scott?
Yeah, I was just going to comment on the lights. Like, I don't know if it would be enough, but you know how being able to see those is kind of important. maybe all that extra heat from the incandescent bulbs can keep it from freezing, and like when it gets ice on it, like if it gets too thick, it's kind of hard to see, or it might make it not work. So that extra heat could be useful.
Yeah. Okay. I don't know that ice-covered stoplights was ever that much of an issue, but you're right. I mean, if they were, that would keep the ice melted.
I've seen
So
them
if
for-
everything has like a specific frequency, and it can fight against like different, like a frequency that doesn't match, does that mean that, like if I had UV light, shining on something and it spat out something else, that if, I shot out something, if I shot like a FM radio wave at it, that it would shoot out something besides heat? Okay, so I mean,
Yeah,
depending on what
yeah.
you shoot out.
And what ends up happening if it re-emits, it always re-emits something of the same energy or lower.
Okay.
So you can't shoot an infrared in and get a gamma ray out. The energy, you never create energy. You can't create energy out of nothing. So the energy, the photon that you come out, if it's not a twin, it'll be a lower energy photon.
So it won't always necessarily be heat, it could be almost
Right.
anything.
Right.
Okay.
Yes.
Something to go for Dallon's idea, can you, like, if you shoot them fast enough or they come in close enough, can you put in like 2 infrared waves or, well, protons and get out 1 gamma ray or
Nope.
something?
And again, we'll talk about why in the quantum unit, but it turns out the answer to that is no.
If, like, can you, are there like substances where if you put in like ultraviolet radiation and stuff like that?
Say it
or
again. I didn't hear you.
Are there substances, like if, like you have like a sheet of material and like you put in like infrared, yeah, UV or anything like that, like you get out visible light, like something will shine if high radiation is put on it?
Yeah. And again, we keep getting into examples that I'm going to talk about in the quant unit. But do you guys remember there used to be some detergent that always advertised they made your brights brighter and your whites whiter?
Yeah.
Okay. What that one did, it had a chemical that was mixed in it that was a phosphor, so that when ultraviolet light hit it, the material would absorb ultraviolet and re-emit energy at a lower frequency. Well, the lower frequency is in the visible. So if you shine ultraviolet light on it, it would emit visible light. And so if your shirt had been washed in this stuff, well, normally ultraviolet light that hits this shirt, bounces off again or re-emits as ultraviolet, which we can't see anyway, so no change. But if the ultraviolet that hits this, and there is ultraviolet light hitting it, re-emitted in the visible part of the spectrum, well, this would appear to be brighter than it would be otherwise. And so the whites appeared to be reflecting more light because they actually were taking the ultraviolet and re-emitting it as visible. And so the color, everything really was whiter and brighter with that because the phosphor was taking the normally invisible ultraviolet light and re-emitting it in the visible wavelength so you could see it more. And sometimes they'll do that with toothpaste also because it wants your teeth to look really, really white. And you can always tell if somebody has that kind of toothpaste if you shine a black light on them. Black light has a lot of UV. And so, if you smile in ultraviolet light and your teeth just really glow, it's because you have that toothpaste that'll have a phosphor in it.
So that would
And
explain.
it re-emits the ultraviolet in the visible wavelengths.
That explains why, like, when you're under black lights and like maybe you're roller skating or whatever, some people like keep their mouths in glow.
Yeah, yeah. And some clothes will glow brightly under black light because they have the phosphor or the dye that's in them absorbs ultraviolet and re-emits in the visible.
So is that like safe? I guess that it's absorbing all that like UV or whatever.
Yeah.
It isn't any different than
A story from physics in real life. I can still remember when I was in first grade. You know how when you're in first grade, there are always little things that the teacher does that everybody, I want to do that one. I want to be the line leader. I want to be the, whatever it is. And in first grade, I can remember there were several little chores that you always wanted to get to do. And one of them, everybody had to get a vitamin every day. So if you got to be the person who passed out the vitamins, that was a big award. And then we also had health lights. And there was a switch on the wall that you're supposed to turn the health lights on for 10 minutes every day. And that was always a thing, if you got to be the person to turn the health lights on, well, you got to go over and flip a light switch is what it was. But, if you're in first grade, that's a big deal. And so I can remember that, I guess that's probably why it made an impression on me that I remember it, because, you know, if you got to turn on the health lights, and nobody ever questioned it, and later on, I, you know, started wondering, well, I wonder why they had health lights, and I wonder why they turned them on for 10 minutes every day. I just wondered what was going on with that. And then as I learned more about physics, I realized what was going on. Those lights, I remember them being kind of purpley looking. So basically they were light bulbs just like this, but they didn't have the phosphor on the inside, so they emitted a lot of ultraviolet light. So ultraviolet light is harmful to biological things, like bacteria, stuff like that. So I'm sure somebody got the idea that if we shine ultraviolet light, it will tend to kill bacteria. It'll be like a disinfectant. And if we do that in the schools, then our kids are going to be less likely to get sick, our kids will be healthier. We only turn it on 10 minutes a day because we don't want to overexpose the kids to ultraviolet light. So I'm sure that some salesman got that idea and sold the school on the idea that your kids will be, your students will be healthier if you shine these health lights for 10 minutes every day. Because I never saw them anywhere else later on, and thinking back on it now, I think it's probably kind of a silly idea. But somebody probably convinced the principal or somebody that that would be a healthy thing for the kids. So you know, it's kind of that same concept that you're asking on.
What, conning people?
No, about taking ultra high energy light and re-emitting it and using that energy to do something else, like in this case, kill bacteria.
Yeah.
The blue LED was made in 2002.
2002.
So 11 years ago.
So, yeah.
The guy made
Time
$200
flies as you
million.
get older. See, that's one of those things I would have thought, oh, that's probably in the last 3 or 4 years.
That's a lot.
But 2002, that's, you
Still
know,
a lot.
that's 11 years ago now. All right. By the way, that's the kind of thing that maybe you guys can take advantage of situations like that I was not able to. When that happened, I remember reading in the technical journals that they can now, that could produce blue LEDs, and I knew, well, immediately, if you can produce red, green, and blue LEDs, you can produce true color. There's going to be a big boom. If I had money, I would invest it in this company that produces blue LEDs, but, you know, I'm a teacher, didn't have all that much money at the time. But